All right, guys, so today's Friday. We have our last kind of video lecture for the week. Hopefully yesterday went well with Mr. Fields and the tiling project. I think it's really cool and very applicable. I know I just did some designing this summer, not necessarily tiling bathroom, but setting up some grid work on my backyard. And I had different choices at Home Depot or Lowe's on which type of tiling fit better for my garden. So I know it's applicable, maybe not when you're 15 years old and you don't worry about tiles, but when you grow up and you have to design something for your house, you will use it. So yesterday was all about 2D and tiling. Today we're going to look at wasted space, or overflow if you will, in packaging in 3D. You guys know I'm the tennis coach, so one of the big time problems we're going to look at today, is when you have a cylinder and you package inside that cylinder 1, 2, 3 tennis balls. So these are supposed to be three-dimensional shapes. 3 tennis balls. Yes, 3 tennis balls fit inside the cylinder or the can, but look at all of this wasted space surrounding those balls. So when they ship them, from the tennis warehouse, they're shipping 3 balls in a canister, but when all the time when you go to the postal service or whatnot, it costs money the more it weighs. Well, they're shipping a lot of red, empty airspace that costs more for them. So is there a more efficient way to design a can that has less material for the can and less wasted space on the inside? If you're not a tennis player, I bet a lot of you maybe have had a Pepsi or a Mountain Dew or a soda, and think about those. A lot of those come in boxes, and let's say about a 6-pack, and maybe they come in a box. 1, 2, 4, 5, 6, and here are your 6 cans. Okay, something like that. Well, just on the top, you can see a lot of the wasted space. And not only is it just up top, then it goes all the way down. There's all this empty space surrounding the 6 cans that come in the box. And our goal today is just figure out how much wasted space is going on there. Is there a more efficient way to design these things? Okay. So with the worksheet that the sub will hand out today, I want you to flip to the back side of it. I want you to try out this one. This has Tic Tacs. There are 60 Tic Tacs that come in a container. The volume of each Tic Tac is 0.855 centimeters cubed. And the little box has the dimensions provided. I'm curious how much wasted space there is. So why don't you take a moment, hit pause on the video. Shouldn't take you too long because getting the numbers are pretty quick. But think through this, take a couple minutes, try it out. When everyone seems to be ready, we'll take a look at my answers. So hit pause. All right, so let's take a look at this question. Here's the first thing I looked at. 1 Tic Tac is 0.855. I know I have 60 Tic Tacs. So if I multiply those together, that gets me 51.3 centimeters cubed. That's how much volume is being taken up by the Tic Tacs solely. Now, a prism or a box, you just go length times width times height. So length times width times height gets me 55.08 centimeters cubed. And if you subtract those, you have 3.78 centimeters cubed of wasted space. Now, you might want to ask, what percent of my total space is wasted? And here, if you take the amount of wasted space, you divide it by the total amount of space, you get 0.069, which is the equivalent of 7%. So that means 7% of the box is air, which means 93% of the box is Tic Tacs. Now I'll tell you this, 7%, that to me, that's a lot of wasted space. You're just wasting space there. It's like you could have fit some more Tic Tacs in there. I'm curious about that actually. How many more Tic Tacs could I fit in there? If this is how much space I have left over, and I know there's 0.855 for one Tic Tac, if you divide those, 3.78 divided by 0.855, oops, 3.78 divided by 0.855. Apparently I could have fit 4.42 more Tic Tacs that I could have fit. Now I didn't fit that, and instead I fit empty space in there. But you're going to be fascinated when we look at the soda cans or when we look at the tennis balls, how much is actually wasted. It is insane. So for us to do some of that, we need to just make sure we remember the volumes of different shapes. And you should have done a lot of this work on Wednesday with the volumes of prisms and pyramids and cones. So remember, volumes of prisms are area of the base times the height. Those are the boxes, those are the tents, those are the cylinders. A lot of people forget what the volume of a cylinder is, but I just look at it and go, what's the base here? It's a circle. That's pi r squared. So if I want volume, it's pi r squared times my height. Too often kids are like, pi r squared, pi r cubed, I don't know. It's a circle times height, that's it. So you should know what the area of a circle is. When it's pyramids or cones, it's the volume is the area of the base times the height, but make sure you divide by 3. So like for this cone, a lot of kids forget what the equation for the cone is, but the area of the base is pi r squared. The height is h, and since it's a cone, you divide by 3. Okay. Volume of a sphere is 4 pi r cubed divided by 3. So those are the guys that we might need to use when we solve a problem like this one. Flip to the front, and we have a problem here. I'm going to fit 8 balls inside a box. Okay, it's kind of cool. There's that blue shape in the inside of that is actually, you can fit a ball inside those 8 balls, or kind of in the wasted space. But for right now, we're just going to say you have the 8 balls. Okay, so think of the 8 tennis balls now in a box like that, or actually a bocce ball. If you've ever played bocce ball, a lot of times they set it up in this fashion. So I want to find the volume of the box. I want to find the volume of each sphere, find the volume of all the spheres, and then what percent of the box in this case is used. I can easily phrase this question as what percent of the box is not used. Okay. So the key thing to this problem is I tell you the diameter of a ball is 10. So if I want the volume of the box, I'm hoping you can see that if that's 10, and then there's another section of 10 for the next diameter, that would make a grand total of 20. And you would have it backwards as well, and you would have it as high as well, because you could see there's 10 and there's another 10. 10 and 10 make the 20. So the volume of the box would just be 20 by 20 by 20, which is 8,000 centimeters cubed. Okay. The volume of a sphere is 4 pi r cubed over 3, which is 4 pi something, something cubed over 3. And that something in this case is not 10. It is 5, because remember, you need to use the radius, not the diameter. So I want to put a 5 here. So I go 4 times pi times 5 to the third divided by 3. I get 523.6 centimeters cubed. Okay. Now it says find the volume of all the spheres. Well, there's 8 of them, so 8 times that 523.6. 523.6 times 8. 4188.8 centimeters cubed. Now this last question says, how much of the box is being used? So if you want being used, you can take, well, I know I'm using 4188 over 8, and I'm going to divide out my grand total of what I have, and this is what's going to blow your mind. 4188.8 divided by 8,000 is 0.5236, which is 52% in use. That means 48% wasted. It's basically a 50-50 here, where you use half of the box and you waste half of the box. There is so much dead space in this box, like that big blue ball that you can kind of see in the middle, that's wasted space. And everything kind of surrounding the other balls is wasted space. So with the Tic Tacs, it was only 7% wasted. Here, 48% wasted. That is insane. So now let's take a look at the tennis ball problem, okay? So I have tennis balls. These are now measured in millimeters, if I remember right. These are in millimeters on your worksheet. And so it is 67 millimeters is the diameter, and 201 millimeters is your height. And I want to do the exact same problem that we did, where I want to find the volume of the can and the volume of the 3 balls, and kind of compare what is being used and what is being wasted. So why don't you here hit pause? I want you to try this out, and then I'm going to reveal how I did it on the next couple minutes of the video. But hit pause first, try it out, and then hit resume when you're ready. All right, so 67 is the diameter of one of the balls. So you need to make sure right away you divide by 2 and get 33.5 for the radius. Don't round that to 34. You would be immediately way off on all of your work. Keep 33.5. Can volume, it's a cylinder, so it's pi r squared h. So pi 33.5 squared times the height. I get that massive number. This would be in millimeters cubed. One ball, 4 pi r cubed divided by 3. You get 1,57479 and change. So then 3 balls would just be multiplying by 3. So you get 472,437. If I want to know what percent of it is being used by the can for the balls, you take what you want, the 3 balls, divided by the total. I get that, which is 66.6% in use, which means 33.3% of it is wasted. You should recognize those as fractions. 2/3 of the can is full of balls. 1/3 of the can is wasted. So 2/3 of the can is full of balls. 1/3 of the can not full of balls, empty. Okay. So again, Tic Tac, 7% wasted. That Bocce ball set, 48% wasted. This can of balls, 1/3 or 33% wasted. Again, you should notice there's a lot of wasted space out there. So because of that, I'm curious if there's a new way to design a can of balls. No matter what, the height or the depth of the can is going to be 201, because you're always going to fit 1 ball in there, 2 balls in there, and 3 balls in there. So those 3 balls, remember, if 1 ball has a diameter of 67, then another ball has a diameter of 67, and another ball has a diameter of 67. 67 and 67 and 67 make the 201. That's why the height or the depth of it is 201. I'm curious, what happens if instead of the whole idea of making it with a can, I'm wondering if we do it with triangles, like a triangle tent, or if we do it with a pentagonal tent, or if we do it with the hexagonal tent, if we can get a better design with less wasted space. Okay, So let's take a look at one. I don't know. I'm going to pick one of these. Let's do the triangle one. Okay. So I know the radius is 33.5. And just like what we've done on Tuesday's worksheet that you did with Mr. Fields and that you kind of rehashed a little bit yesterday with the tiling stuff, we should be able to set up and find the area of the triangle. So if that's 33.5, then I could draw in, let's see, I'm going to try and draw them in for you so you see it. I could draw in lots of different triangles here. And we are going to find the area of this green triangle. If we find that area, we can multiply by 6 of them because there's 6 of those green triangle. So remember then we would do 360 divided by 6 equals 60 degrees. So that means in this triangle, I have 60 degrees right here. This length is 33.5. And this length, I don't know. So we'll call him X for a moment. So now I could do tangent of 60 degrees equals X over 33.5. Notice here, unlike Tuesday, where Tuesday you were trying to find the apothem or the red side, but you knew the black side. This time you know the apothem, you just don't know the outside or the black side there. Well, we can get that, so it's just more trig stuff. So I got tangent of 60 times 33.5. I get X to be 58.02. Okay, so if X is 58.02, the area of one guy would be 58.02 times 33.5 divided by 2. 58.02 times 33.5 divided by 2. And I get area is 971.835. Now realize that's the area of one green triangle. So you're going to want to multiply by 6 green triangles. So I get times 6. And the total base, or the total area, is 5831.01. That is the total area of that triangle. Okay. Now, if I now want, let me put that in here so you see a little bit better. 583101. If that's the area, remember how thick or how deep is the tent? It was 201. So if this is the area of the base, the area of the triangle, to get the volume, you would do area of the base, 5831.01, times the total height, 201, times 201. You get 1172.033.01. Okay, that looks huge, but let's see how that compares if it's bigger or worse than this guy. The can volume was 70656, and the total of 3 balls is this. And now I discovered, at least for this can, that its total volume is a little bit different, but it's that. Okay, so far I have the tennis balls 3 will always be that amount, and the prism is the one that I just did, is that amount. What else is there? The cylinder was that amount. The only 2 that I don't have you have yet are the pentagonal and the hexagonal prism. Now I'm showing you the answers right now, but I want to see if you could get those answers, okay? So remember, you do area of the base times the height. The height of each one's 201. I'll start you on the pentagonal one. You can draw down, that's 33.5. I would then, if you want, draw. You could now draw this triangle. How many blue triangles are there? Well, if there's 5 red triangles, there should be 10 blue triangles. So 360 divided by 10 is 36. The 36 there. That should give you enough info to get the x, then find the area of the blue. Multiply it by 10 to get the area of the whole pentagon. Then multiply by 201 to get the entire volume of the pentagonal guy. And you can do the same with the hexagon guy. So right now, I want you to practice that. Here are the answers. I want you to hit pause and make sure you can try and get those answers by trying it out with your friends for the pentagonal and the hexagonal. If you round, you might be off by a lot. Last year, a student rounded early and got 823,000. That's pretty close. I know you're doing it right. You just rounded. So don't round right away. Round a little bit later. Okay? So try this out. Hit pause. All right. So on this, hopefully you got those. And if you're trying to figure out which one has the least amount of wasted space, well, if I'm only trying to fill up 472, 437 volume of balls, the one with the least amount of space still happens to be the cylinder. But we already found out earlier that it was 2/3 used and 1/3 wasted. So even though that's the best one, it's still not the best because there's still a lot wasted on that. Hopefully those are some practice problems for you. There's more of those in your homework tonight. Let's take a look at surface area of a sphere. If you've never written this down or never seen it before, the surface area of a sphere is 4 pi r squared. It's kind of cool. The area around a ball is 4 areas of circles. If you ever took an orange and tried to peel it and never ripped any of it, the orange peel could fill up 4 circles, which is kind of neat. Okay, so surface area of a sphere is 4 pi r squared. You're going to want to write that down somewhere else in your notes. Okay, and then we're going to try some problems out. First one, super easy. Find the surface area. I give you a ball with diameter 10. So immediately I change my diameter to a radius of 5, and I go 4 pi 5 squared, and I get it. Now, if these are in inches, and these are in inches, then your surface area would be in inches squared. Okay. Last problem before you get to work on a worksheet is one like this. Suppose I give you a surface area of 200, and I want to know the volume. So the question would be, what's the volume of a ball whose surface area is 200? Well, in this whole thing, the key to this whole thing is connecting it with the radius. So if I know the surface area is 200, let me write this. Surface area is 4 pi r squared. That's what you wrote before. So I can now say 200 equals 4 pi r squared. Let's get r first. So let me divide by 4. So I get 50 equals pi r squared. Let me divide by pi. It's going to be ugly, so let me just write it like this first. 50 divided by pi equals r squared. Now that, let's just get that, 50 divided by pi, that's about 15.915 equals r squared. Square root it, r equals 3.989. Okay, so if you want, let's just roughly say that's 4. Now that you know that the radius is 4, you can go get volume, because volume is 4 pi r cubed divided by 3, because now instead of an r, I know the r is 4. So now I can go 4 pi 4 cubed divided by 3. Now I get 4 to the third times 4 times pi divided by 3. I get 268.08. Let's say these were all in inches, then this would be inches cubed. So the key of bouncing back and forth between surface area and volume is getting the r. Tonight's homework, which you'll have a lot of time in class, is going to be finding volume and surface area of spheres, and then working with wasted space and seeing how much wasted space when you design canisters for tennis balls, or maybe it's racket balls this time. And also maybe a wasted space when you stack a lot of coins in a box. Okay, the homework's online. You can take a look at it, and it will be due on Monday. I will be back on Monday, and I'll give you a full update report on my son or daughter and the health of my son or daughter and the name of my son or daughter, as we should have hopefully delivered healthily earlier this week.